Welcome back. You have to imagine that in a solar plant there is the possibility that some modules may cast a shadow on the other modules placed behind, and this can happen in different moments of the day and of the year. In this video we will look at this problem and give you some design guidelines how to use the area available for your PV system. So the learning objectives of this video lecture are to understand and determine the optimal mutual spacing of PV modules using the calculation of the shade-free time window, the row spacing between PV modules, the ground coverage, and the PV yield per functional area. So let's get started. These two representations are an example of the same PV system composed by two rows of identical modules with identical tilting angle and position. The only difference is that they were obtained by simulating the sun in two different and opposite periods of the year, winter and summer. In winter, on the left-hand side, the position of the sun is low on the horizon, and thus the shade casted is much longer compared to a typical day of summer as the one simulated on the right side. So the length of the shadow is different during the year. This aspect has to be taken into account during the design of PV systems because it might happen that during winter rows get mutually shaded, lowering the yield of the system. Therefore, an optimization is needed to avoid accidental shading among the modules, which leads to an underperforming system, but also to avoid overcompensation, which increases the land or roof usage. Since the length of the shadow is the longest when the sun is the lowest on the horizon, reaching its minimum on the 21st of December on the northern hemisphere or June 21st on the southern hemisphere, it is common practice for installation companies to design and optimize the PV system for a shade-free time window on this date. Normally this shade-free interval is an input from the customer which needs, for example, the maximum power achievable by the system from 10 a.m. to 2 p.m. Then, based on this input, the engineer calculates what should be the inter-row spacing. Let's see how to do it. First, we have to determine what the sun elevation angle is going to be, and we will use this graph with the solar azimuth versus elevation at a certain location on Earth, for example in Delft in the Netherlands. The 21st of December, which is the solstices of winter, is represented by this blue line on the bottom, while the top curve is the solstice of the summer falling on the 21st of June. We can also identify the analemmas for every hour. Note that the analemmas are here reported as a continuous single line. At this point we select the shade-free time window between 10 a.m. and 2 p.m. and we want to ensure that the rows are not mutually shaded on the solstices of winter. Starting from this window highlighted in the chart, we can draw a horizontal line out to the left of the chart that points to the solar elevation angle at those specific moments. In our case, it is estimated around 10 degrees angle, which will be used next to determine the module row spacing. Let's now look at this trigonometric system here. We are going to derive the equation of the row spacing starting from this simple trigonometric relation where D is the row spacing, and it is obtained by adding the vertical projection of the module where L is the length of the module and theta m is the tilt angle of the PV module. The second term is also called D shadow, obtained with the vertical projection of Z, which in turn is the distance between the top edge of the module and the end of the shadow on the ground. We can arrange this equation and write Z as a function of the height h of the module. Then sinus divided by the cosine can be written as the tangent of the sun altitude, and finally h can also be expressed as a function of the module length and the tilt angle. To summarize, there are different ways to express row spacing d as a function of the length of the module. tilting of the module and the altitude of the sun, and all these equations are equivalent. The next step in the design is to account for the azimuth angle, and thus we will use again this figure to draw two vertical reference arrows down from each time reference. The azimuth values are 152 when it's 10 a.m. and 208 degrees at 2 o'clock in the afternoons, so we will use these data in the following formula to determine the minimum module row spacing. Here you can see the final equation with the azimuth correction highlighted in red. Once you plug all the information required, you will know the value of D, for example, at 10 in the morning and 14 p.m. in the afternoon, and you just have to pick the biggest distance among them, and that will be the distance among each row of PV modules. However, for a first quick estimation, one can use the rule of thumb that the distance between the two rows of modules should be at least 3 times the length of the module. It is important to note that the module spacing plays an important role also in determining the surface area required for the installation. Therefore, we introduce a parameter to measure the land occupation. Such a parameter is called the ground cover ratio and is defined as the ratio between the area of the PV array divided by the total ground area, which could be the area of a roof or a field. GCR is strictly related to the tilt angle because an increase in tilt requires row spacing to increase to avoid inter-row shading. So lower ground cover ratio values will keep modules spaced far apart, which maximizes their individual energy yield, but will result in a smaller sized system installed capacity. On the other hand, higher ground cover ratio values will increase the system size, but will also reduce the energy yield from higher mutual shading. The role of an engineer is to find the optimal tilt and ground cover ratio combination for maximizing the output for a system, or in other words, to find the trade-off between the system size and its energy yield. So far in this video lecture, we have considered the traditional glass encapsulated panels and discussed their mounting strategy in terms of mutual spacing, ground cover ratio and energy yield. However, if we would consider a flexible solar fall product, the mounting strategy can become significantly different. These modules can, for instance, cost-effectively glued to a facade or flat roof surface with extreme high surface cover ratios. Money can be saved as less mounting material is needed. In addition, the modules do not need mutual spacing and are less sensitive to mechanical stresses, which means installers can walk over them. Although these type of module products might have a lower module conversion efficiency, due to the high ground cover ratio realized, the total yield of electricity per functional area of roof or facade might be even higher in reference to PV systems of glass encapsulated modules on the same functional area. An important takeaway is that comparing such diverse technology, it becomes more important to compare the PV system yield per functional area than looking at the module conversion efficiency. In summary, in this video, you learned for a PV system based on rows of glass encapsulated PV modules how to graphically locate the solar azimuth and elevation for a specific shade-free time window. Then with these data, we derived the trigonometric formula to obtain the inter-row spacing, the shadow, and lastly we defined the ground cover ratio parameter to evaluate our PV system design. However, we also have discussed that if new PV module technologies as SolarFall are considered as well, it becomes more important to compare PV system yield per functional area than using a metric like the module conversion efficiencies. In the last 4 videos, we have focused on the location and orientation of PV modules in a PV system. In the next video, we're finally going to design a PV system, so see you in the next video.